So we've looked at a case where this is not true, where the events are dependent, so that we can see above that the events are dependent. That's not independent. And L and Q1 are dependent. But let's look at the probability of it being on the left, given that it's on the bottom. Let me draw those picture of this. Here's our big sample space size with 10 and 20 squares. And so here is left, and here is bottom and bottom half. Okay, so we want to know what's the probability. This is defined as the probability that L intersection B divided by the intersection of B. Well, what's the intersection of L and B? Well, that is just this little portion here. So it's 1/4 the area, because this is 1/4, 1/4. This is like one left and right is 1/2, bottom is 1. So that's 1/4. So this is going to equal this is going to equal 1/4 over the probability of B, which is 1/2. Now, if you remember your fractions, this is 1/4 times 2 over 1, because you divide fractions, and the rule is that you flip them over. That's one way to think about it. So that's equal to 2 over 4, which equals 1/2. So the probability of the left given B equals 1/2. Okay, but what's the probability of L? Because if you want to see if B and L are independent, we have to do L. Well, L is going to be just 1/2. It's the left half of this box, because it's like 10, but this is 20. So this is 10. This is like 100 divided by 200, or 1/2. So we see that probability of L and B is equal to the probability of L. So L and B are independent. Now, this is interesting because they intersect, right? Now, up here, Q1 and L are dependent, but they intersect. L and R are dependent, but they don't intersect. Their intersection is 0. So independent events their intersection can't be 0 if they're going to be independent. And it doesn't necessarily mean that all where the intersection is where there is an intersection, it's not 0, that somehow they're independent. It has to do with the way that they intersect. Like, in some sense, these intersect in just the right way. They're sort of perpendicular to each other in some sense. Now, it doesn't mean that if there is an intersection here, there's another. To contrast this, let's look at the probability that it's in well, let's see. I give an example in the text, and so maybe it's good to give that example in the text. It's this one here. We want to give the probability it's in the left, given that it's in the bottom diagonal. This is in the left, given that it's in the bottom diagonal. Well, that's going to be the probability of the intersection of the two over that. Now, so let's see. This is going to be the sort of size of that over the size of the diagonal B. And you can see that if this diagonal is going to divide the whole space in half, if there's 200 squares in here, this is going to be 1/2 that, or 100. So this is going to equal something over 100. Okay, but what's the intersection of L and this? Well, it's this sliver here. Now, since this came down halfway, this this sort of triangle is going to be 1/4 of the L. It's going to be, instead of, there are 200, this is like 100, there's going to be 50 up in this square, and there's going to be then, there's going to be 50 up here and 50 down here. So half of 50 is 25. So this is going to be 25 over 100, or 1/4. But the probability of L as before is 1/2. Therefore, the probability that the left occurs, given that it's in the lower diagonal, is not equal to the probability of the left. So L and DB are dependent, because in some sense they don't intersect in sort of a perpendicular way. So independence in terms of these set diagrams is a little mysterious, but that's why it's hard to just look at the sets and think about whether they're independent or dependent. Sometimes you have to do the calculation to see that they're whether independent or dependent events. Okay, well, now we're going to do, I think, some exercises to see if you can understand this. Let's look at exercise 12 on page 279. Which is, it asks here, let's see, we have two events. We don't know what the overall context is. We know that the probability of A equals 1/3, the probability of B equals 1/3, and the probability of A intersection B equals 1/6. So the question is, are events A and B dependent or independent? So you would circle one of these if you were doing this on your PDF. So I want you to do is pause the video at this point if you're listening to this, or in real time if you are to recording. Okay, so here is how you do that. Here's how you figure out this exercise. You first calculate the probability that A occurs given that B occurs. Well, that is by definition, and this is what this problem is about, just remembering the definition, the intersection of A and B divided by the probability of B. If you wanted to remember this, it's always the second one that's the denominator. So the two of them go up top, and the sort of the bar becomes this intersection. The bottom, the second one goes to the, okay, well, I've given you this. This is 1/6 over 1/3, which equals 1/6 times 3 over 1, which equals 3 over 6, which is 1/2. And the probability of A equals 1/3, which is not equal to the probability of A given B. So A and B are dependent events, in the sense that that you can see that the probability that A occurs is just 1/3. But if we know that B has occurred, then that's going to increase the chances. The chances of A goes up to 1/2. So that means that knowing that a dependent event means that if you know that's occurred, that gives you information. There's an interaction between the two in the sense that you know that B has told you something about whether A occurs. It's increased the chances that A occurs. Okay, so let's go on to the second one, which is verify your answer to the previous question by finding the following conditional probabilities. So let's take a moment and do that. I'm going to pause the recording, and you should pause the recording too if you're listening to this. Okay, well, by the definition, this is going to be the probability that A intersection B occurs over the probability that A occurs, well, and that's just going to be the same thing because it's 1/6 over 1/3, which equals 1/6, 3 over 1, which equals 1/2. And so this is so you can see that this is sort of coincident with the fact that if A and B are independent. Now, this doesn't necessarily, I mean, they're not independent, they're dependent, but this doesn't necessarily mean that these are the same. Let me see if we can think up an example. Oh, well, I think we have an example here. Let's look at the example. See, these ones, the two probabilities are the same. Here, we have different probabilities for 1/3 and 1/2. So let's now work on problem 14, in which we know that the probability of event A is equal to 1/3. The probability of event B equals to 1/2, and the probability of the intersection equals 1/6. So the question is, are events A and B dependent or independent? So pause the video if you're listening after. Now, so we do the same thing of look at probability of A given B, say, and that's going to be the probability of the intersection over the probability of B, which equals 1/6 over 1/2 now, which equals 1/6, 2 over 1, which equals 1/3. So the probability of A given B equals 1/3, which equals the probability that A occurs, right? So that would seem to suggest that they're independent. Now, the reason for looking at them both ways, if these events are dependent, neither of these should equal, this should not equal P of B, this should not equal P of A. And that's what actually occurs, because up here P of BA is 1/2, and the probability of probability of B is 1/3. So the fact that neither one of these is equal to probability of A or probability of B confirms that A and B are dependent. But here it's sort of a question is it really going to be? What about this? There's two ways I could check whether these were dependent or independent. Well, this is going to be the probability of A intersection B over the probability of A. Well, the intersection is 1/6, and then probability of A was 1/3. So this was 1/6, 3 over 1, which equals 1/2. So the probability of B given A equals 1/2, but that equals the probability of B. So even though that the numbers here are different, in other words, that somehow A and B are independent. So it's not completely clear, in other words, you need to go through the calculation, because it's not completely clear when you have something that's dependent. And maybe this was just a special case, that if I did this as instead of 1/3 and 1/2, it was 1/4 and 1/2. We could try that and see. For example, let's in fact, and that's what we want to verify here, that if this should equal the probability of A, this should equal the probability of B, and that's what happened. And so that confirms that A and B are independent. Let's do one more exercise like this.
I have a question.
Okay.
I thought the definition of independent variables would mean that they would equal the denominator, not the other number.
Oh, no, they're equal to the first one. In other words, if the probability, the definition, let's go up and look at the definition. The definition is, where do I have that? See, it's the first one. So knowing, this is the one this is the one you're trying to
Oh,
predict.
okay.
So the point is, if knowing B occurred does not affect whether the probability that A occurs, then A or B independent, because it's sort of like independent events are such that if you know that B occurs, you have no information that helps you, increases any information, that doesn't give you any information whether A occurs.
Hmm.
So it doesn't help you if you want to know whether A is occurring and someone says, well, B occurred, and so well, it doesn't really help me because these two probabilities, that A given B and probability of A are the same. So
Okay.
so in some sense, it's like, that's why, in fact, that's why this last one sort of works, right? Because here in the denominator, you had B, and they were different. So you had 1/6 over 1/2 is 1/3. So that you notice here that in this particular case, they're independent, and the probability of B given A equals 1/2, but the probability of A given B is equal to 1/3. They're not the same.
Hmm.
So that means that it's strange in the sense that you know, it's like it's a little mysterious. So conditional probabilities are not necessarily intuitive because they're telling you about some strange interaction between these
So,
two.
so if the answer equaled either A or B, they would be independent events, or what if the
Well,
answer was
they're independent because the probability of B given A is equal to the probability of B.
right?
That
But
alone, and then also it has to be the probability of A given B equals probability of A. So
mhm.
those two, so the problem is, I can't, if these have to both be true, in other words, this connection they have both, even though the number is 1/3, it's not equal to 1/2, you have to have this connection. Both of them have to work for the events
and
to be independent.
I understand that. What my question is, if the answers were different. So if the probability of A given B equal the probability of B, would that be so
Oh,
for the
well,
first one?
let's look. The question is, if the probability, you're interested in the question, if the probability of, say, B given A equals the probability of A, right?
Yes.
Okay, well, let's see, this is interesting because let's see what this is the probability of the intersection of A and B over the probability of A, right? And if that was equal, then it's not clear it's just, you know, it's just like some weird connection that
Okay.
it's like, it's not clear what exactly, how, because the probabilities, it's like a weird thing in which um
It would mean B equals A. Okay, I get it.
it may, not necessarily, because if B was equal to A, this intersection would be A and this would be 1, and the probability of A would be 1. So it's not clear what exactly is going on. If this, we would, let's see, in the first case, this happened, right? Because like up here, the probability of A given B equals 1/2, and the probability of B is 1/3. Let's see. Oh, okay. We have to, this is an open question now. What does this mean? Or what if it equals this? I'll try to come up with an example where this is the case. And we'll see what the possibilities are.
Okay, thank you.